Very good morning, my dear students. Okay, coming to the second video. In this video, I'm going to tell you about the problems of step to power. Okay, so in the previous class, in the previous lecture video, I'm going to told about what the single bar element problem. Okay, so here step to bar problem you're going to solve, that is 2 bar element and 3 bar element. Okay, so procedure is same. So something where that global addition of global stiffness matrix is different. Okay, in this problem. Okay, and this is most important question for the point of examination. Okay, so here look at the problem. Okay, 2, that is type 2 problem. Okay, so already we solved type 1 problem. What we did in the type 1 problem is we are going to consider only the single element. Okay, where here there are 2 elements. So this is first element and this is second element. Okay, so there's such type of problems we are going to call as type 2 problem. Okay, that is type 2 problem, nothing but what? Problems on step to bar element. Okay, so I will read the question. Okay, consider a step to bar as shown in the below figure. Determine the nodal displacement stress at each element and the reaction forces at the support using this elimination method. Okay, they are using they are telling that what, use elimination method. You have to solve that to calculate the stress strain displacement. Okay, so what do you mean by step to bar? First of all, step to bar nothing but what, one element diameter is bigger and one more element diameter is smaller than that. Okay, so look at here. So such type of element you are going to call as step to bar element. Okay, so here A stands for area and E stands for Young modulus, and here okay they given separate area and E1, and they are given A2 E2 separate. Okay, here at the middle a force is acting, that is opposite, that is axial force is acting here. Okay, so at node number 2, and one more force is acting F3. Okay, here they are force acting is here. Okay, that is F3 is equal to some force is acting axially. Okay, they given the data, that is F2 is equal to minus 10 kilonewton and F3 is nothing but 5 kilonewton. Okay, so and length of the first element is given 50 mm and the length of second element is 50. The total length is 100. Okay, so first step I told you, first read the question carefully, identify the diagram which type it is belong, according to that you have to solve. Okay, so first here the given Young modulus and area is separate, so you have to write the given data separate only. Okay, that is for the given data for the first element. So for example, it is made up of steel, means for the steel Young modulus is equal to 200 gigapascal. I told you in the earlier class also, you have to convert into Newton per mm square, that is megapascal. Okay, so into 10 to the power of 3 if you make it, means that 200 into 10 to the power of 3 is Newton per mm square. Area for first element is equal to 150, they given in the question. And second element is made up of aluminium, AI nothing but aluminium. So Young modulus for the second element is 70 gigapascal. Okay, 70 into 10 to the power of 5 Newton per mm square, and area of second element is there given 100. So axial load F2 is equal to minus 10 kilonewton. This is minus 10 kilonewton. This is 5 kilonewton. Okay, so this is the given data they given. So you have to use the procedure and solve the displacement. Okay, so look at here, which node is by using elimination method nothing but we are going to delete the known values of that known node values. Okay, that is here node 1 is fixed, so you have to delete the first 2 and first column. Okay, so you have to calculate U2 and U3. Okay, so same first step is what, discretization of finite element model. Okay, so this is the given diagram. You have to discretize the given body or build a finite element model by comparing the given diagram. Okay, so this is the first element, this is second element. So first element is consist of what, so node number 1 2 3. First you have to give the node numbering first. Okay, so this is a bar element, just to draw one line. So node number 1 2 3. Okay, so here node number 1 2 3. Okay, so here this is element number 1, this is node number 1 between 1 to 2 is called as element number 1, node number between 2 to 3 is called as element number 2. Okay, so Q1 stands for what, the displacement at node number 1, Q2 stands for displacement at node number 2, and Q3 is this is the Q3 stands for what, displacement at node number 3. Okay, so length L1 L2, so F1 F2 F3 force are given. So this force direction should be this side, but I shown this side. Okay, so here see the symbol here, force direction is this side, you have to show this side only. Okay, so that is F2, I will tell here it is a mistake. Okay, so direction should be this side, opposite, it is near to the node number 2. Okay, so this is the discretization of the given model, that is finite element model. This is the first step. Okay, second step is what, calculate the element stiffness matrix. We know that the formula, what is the element stiffness matrix formula, that is KE is equal to AE by L, 1 minus 1 minus 1 1. Okay, so this is the formula for ESM. Okay, that is element stiffness matrix. Okay, since here two nodes they see two elements are present, so you have to calculate K1 and K2. Okay, so K1, that is the element number 1 node between 1 to 2, that is element number 1 nodes are 1 to 2 and element number 2 is 2 to 3. Okay, so now calculate that by using those formula, that is K is equal to AE by L, 1 minus 1 minus 1 1. Okay, substitute all the formula here, that is a given data, substitute in this, we are going to get the 150. So this is the area 150, Young modulus is 2 into 10 to the power of 5 divided by length is 50, 1 minus 1 minus 1 1. Okay, simplify this, you are going to get 10 to the power of 5 into 6. So 6 you have to multiply in this inside the value, that is matrix. So you are going to get 10 to the power of 5 is equal to 6 minus 6 minus 6 6. Okay, node number is 1 2 1 2. These are called as global node degree of freedom. hidden. Okay, why it is called, I mentioned here q1 2 because element number 1 is consist of node 1 and 2. Okay, similarly you have to calculate the element swiftness matrix for 2. K2 is equal to A2 E2 by L2. So substitute A2 area is 100 and Young modulus for second element is 7 into 10 to the power of 4 and length is 50. So if you simplify this, you are going to get 1.4 into 10 to the power of 5. That 1.4 have to multiply inside, so outside is 10 to the power of 5. 1.4 minus 1.4 minus 1.4 1.4. Okay, so since it is element number 2, so you have to write the degree of freedom is 2 3 2 3. Okay, so this is the degree of freedom for the second element. Okay, so coming to the next step, that is a global swiftness matrix. That is a global swiftness matrix. What is a global swiftness matrix? So it is a combination of these two. You have to add both the element. Okay, so k is equal to k1 plus k2. Since since in this problem the maximum node is 3 here. Okay, so you are going to get 3 into 3 matrix. Okay, so k is equal to 10 to the power of 5. This is a 3 into 3 matrix. So write 1 2 3 1 2 3. That is q1 q2 q3 q1 q2 q3. So how to write these values inside? 6 minus 6 so 0. Okay, so look at the q number 1 position is 1 1. So 1 1 you have to check in the both the matrices. 1 1 1 1. Okay, so 1 1 is 6 here, 1 1 is not there, so 2 3 is there, so 6 plus 0 is equal to 6. Okay, again same minus 6 q2, so q2 that is minus 6 is equal to q2 q1, that is 2 and 1, 2 and minus 6 is there here, not there, 2 1 not there, so minus 6 plus 0, so minus 6, so 0 3 1 3 1 not there, 3 1 not there, 0 plus 0 is equal to 0. So I wrote here 7.4 here. How? 2 2, so 2 2 2 2, so 6 7.4 like that. You have to you have to write this global swiftness matrix like this. Okay, you have to add these matrices according to the node number, not for the values. Okay, according to the node number you have to add it. Okay, so this step is called as a global swiftness matrix. So coming to the next one is find the nodal displacement. So here since 3 elements are there, so that is q is equal to q1 q2 q3. q1 q2 q3 is nothing but what? The displacement. Okay, global load vector is equal to, since 3 nodes forces are acting, that is f1 f2 f3. So f1 is 0 because it is fixed, so f2 is minus 10 into 10 to the power of 3. So force is acting opposite here. Okay, look at the diagram here, the force is acting opposite, consider as a negative. Okay, so negative sign you have to take a f2 is equal to minus 10 into 10 to the power of 3. f3 is equal to what? 5 into 10 to the power of 3 they given. Okay, now write the equilibrium condition, that is k q is equal to f. So substitute the k value here, q value here, f value here. Okay, so according to the elimination method, applying boundary condition, so first row going to be what? First row it belongs to the fixed one, so have to delete the first row and first column. Okay, so since here in this problem node number 1 is fixed, so this is node number 1, you have to delete this. Okay, if you delete the first row first column, means inside value is what? So inside is you are going to get what? This is 7. I will repeat again. So since this node 1 you are going to delete this. Okay, so inside value is 7.4 minus 1.4 minus 1.4 1.4. Okay, that you have to consider here. Okay, so write as it is. So from since node number 1 is fixed, so remaining is 10 to the power of 5 as it is. Okay, so 10 to the power of 5 and 7.4 minus 1.4 minus 1.4 1.4 q2 q3, this you have to write is it. Okay, so you simplify this, it is 7.4 into q2 minus of 1.4 into q2, minus into minus going to plus, so you have to simplify this matrix. Okay, you are going to get the q2 value is equal to what? This is into is not equal. Okay, so this is q3 is equal to minus 8.33 into 10 to the power of minus 3 and q3 is equal to 0.0727 into 10 to the power of minus 3. So these are the nodal displacement. Okay, so if you write in the matrix form, the standard form, q is equal to 0 minus 8.33 to 10 to the power of minus 3 and 0.02738 into 10 to the power of minus 3. Okay, mm unit is displacement unit is mm. Okay, so like that you have to calculate the nodal displacement of the stepped bar. Okay, this is method is called as what? Elimination method. Okay, so I hope you understand this 2 bar stepped element. Okay, this is most important, nothing is there, just addition of 2 matrices will be there, addition will be there. Okay, coming to the another problem, we are going to solve this. Okay, so this is also very important, this is also a big problem. So now we are going to solve one more problem, that is a 3 bar element. Okay, so second problem, similar procedure same is there. Okay, instead of 2 elements here 3 elements are there. Okay, so find the nodal displacement stress in a thickest section and left reaction of the structure as shown in the below figure. Okay, so this is a diagram they given, so have to read the question properly. Okay, so since it is 3, it is this bar is made up of 3 element, and diameter going to varies, that is area going to varies. Okay, so they given separate data for the each element. So first element length is 80, second element 90, third element length is 70. So first element area is 900, second element area is 400, third element area is 200. So gigapascal means Young modulus they given. Okay, return the given data for each element. So for material 1, E is equal to what? 70 gigapascal, convert into Newton mm square, area 900, length of first element is 80, F1 that is fixed, so consider 0. Coming to the second element, so area Young modulus is 105 gigapascal, you have to convert into Newton per mm square, that is 1.05 into 10 to the power 5, and area they given 400, and length of second element is 90, and F2 this is 20 kilonewton is there, so you have to convert into Newton, that is 20 into 10 to the power of 3. Okay, similarly you have to note down this third element data. Okay, so third element data. Okay, once you note down the data, then go for applying the procedure. That is first step is what? Finite element model. The finite element model can be stepped bar as shown in the below. This is stepped bar problem they given. You have to compare this, you have to build this diagram. Okay, so since one bar element is there, just you want draw one line. So how many elements are there? 3 elements are there. Okay, so this is first node, just you write here first, this is second, third, fourth. First, second, third, fourth. Okay, so since element number 1 you give element number 2, element 3. Okay, so maximum node is here 4 and minimum node is 1. Okay, at node number 1 force F1, and at node number 2 force F2, at node number 3 F3, at node number 4 is F4. Okay, so Q1 is the displacement at node number 1, Q2 is the displacement at node number 2, and Q3 is the displacement at node number 3, and at last Q4 is the displacement at node number 4. Okay, so this is the L1, L2, L3. So this is the minimum is node 1, maximum node is 4. So in the global stiffness matrix you are going to get 4 into 4 matrix here. Okay, so once if you construct this element, then go for calculating the element stiffness matrix for each element. Okay, so we know the element stiffness matrix for a bar element is equal to what? Ke is equal to AE by LE, 1 minus 1 minus 1 1. Okay, this is the standard formula for bar element, that is ESM. Okay, so you have to calculate the each element stiffness matrix. Okay, so we know the area, Young modulus, length we know, so substitute all the values, you are going to get this. Okay, so K1 for first element, this is for first element, K1 is equal to, so area is equal to 900, Young modulus is 70, and L is equal to 80. So this is 1 into, okay, 1 minus 1 minus 1. Okay, simplify this, 10 to the power of 5, you are going to get, after simplify this, you are going to get 7.8 into 10 to the power of 5. Okay, so 7.85 you multiply this inside, you are going to get this 10 to the power of 5 is equal to 7.8 minus 7.8 minus 7.8 plus 7.8. Okay, so since element number 1 is belongs to node number 1 2, so right here global degree of freedom is 1 2 1 2. Okay, similarly you have to calculate E2 E3, and okay, so here only the global stiffness matrix going to changes. Okay, second element 2 3 have to write, and third element you have to write 3 4. Okay, 3 4. Okay, since the third element is consist of what? 3 4, this is 2 3, this is 1 2. Okay, so according to, okay, so after calculating the element stiffness matrix for each element, then go for global stiffness matrix. Okay, so this is very important. Global stiffness matrix nothing but what? Combination of all the element. Okay, so that is K is equal to K1 plus K2 plus K3. So global stiffness matrix you have to add here. Okay, so K is equal to 10 to the power of 5. So maximum node is 4 is there, so you have to write the 4 into 4 matrix. Okay, so one more thing is there, you have to simplify such a way that the outside is 10 to the power of 5 is same for all the element. Okay, like that you have to simplify. Okay, so that you are going to take common here easily, 10 to the power of 5. Okay, so now 4 into 4 matrix will be there. Okay, similarly you have to calculate the addition of this, so that is 1 1 7.78. 1 1 you have to check in all the elements. So 1 1 is only 7.85, this is 0, this is 0, 7.85 plus 0 plus 0 is equal to 7.85. Okay, so this addition matrix you have to know according to the node number, you have to add it. Okay, so I hope you will get this. Okay, if you practice problem you are going to get. Okay, how to write minus 7.875 is equal to this is the position, what node number position is 2 and 1. So 2 and 1 is 2 and 1, here not there, here not there, so 2 and 1 is equal to, so here minus 7.875 plus 0 plus 0, right here minus 7.875. okay, like that you have to write. So this one is 0, I wrote here, Q3 1, so 3 1 is not there, here also not there, and 3 1 not there, here also not there, 3 1 is not there, so 0 plus 0 plus 0 is equal to 0. Similarly 4 1 is not there, 4 1 not there, 4 1 not there, so put here 0. Okay, so like that you have to add the global stiffness matrix. Okay, once you calculate the global stiffness matrix, also calculate along with nodal displacement. Okay, so what is the nodal displacement here? So no number of node is equal to nodal displacement. Okay, since here 4 nodes are present, so here you have to add this, that is what here you have to take that 4 displacement, that is q is equal to q1 q2 q3 q4, this transpose. Okay, if you remove transpose means you have to write vertical like this. Okay, so next global load vector, so f is equal to f1 f2 f3 f4. okay, f1 is fixed 0, f2 they given 20 kilonewton, convert 20 into 10 to the power of 3, f3 is given 10 into 10 to the power of 3. F4 is not given, this is also fixed, you have to 0 here. Okay, so now after substitute all the values in the equilibrium condition, so okay, so you are going to get this. Okay, so now here what you want to do is look at the observe the diagram. Okay, so next step is apply boundary condition by using elimination method. Okay, apply the boundary condition here. Look at node number 1 and 4 are fixed, so delete respective row and column for first row first column like this. Okay, so you have to delete the first row first column, and one more, node number 4 is fixed, so delete first fourth row fourth column. Okay, so remaining inside you have to so this is about what the you have to delete according to the node number. Why we are going to delete first row first column, fourth row fourth column? Because in the observe the diagram, so first nodes are fixed, fourth nodes are fixed, so you have to delete the first row first column. This method is you are going to call as elimination method. Okay, so after deleting, so inside is 12.54, so inside what we are going to get is this 12.5444 that minus 4.66 okay, so this minus 4 and 10.38. okay, so node number is very important. 2 3 you have to write 2 3 only. Okay, so 4 says 2 3, so write the force value 2 3. Okay, so now on simplification this we are going to get q2 value and q3 value. Okay, q2 is equal to 0.0234 and q3 is equal to 0.02 mm. Okay, unit for displacement is mm. Okay, so that is nodal displacement r. So q1, that is q1 is equal to 0, q4 is equal to 0 because it is fixed, so q2 q3 calculated here. Okay, so that is 0.02 0.027. okay, now stress in the each element, that is thickest section, is equal to what? We have the thickest sector, what thickest section is this one, that is the maximum diameter. Okay, so we have the formula for stress element is equal to E1 by L1 minus 1 1 Q1 Q2, that is U1 U2. so substitute formula you are going to get simplify this, stress is equal to you are going to get 20.5187 megapascal or Newton per mm square. Okay, so like that you have to solve the what stress element. Okay, thickest, they are asking only thickest nothing but the maximum diameter. Okay, so now at the last we need to calculate the support reaction. Okay, support reaction formula is equal to what? R is equal to, this is the K Q minus F. Okay, so R is equal to K, this is the formula. R value I will tell you R. Okay, so R value, what is the for support reaction? This is K. Okay, this is U minus of F. Okay, substitute all the values here, so simplify, you are going to get this value. Okay, so that is R1 is equal to what? Minus 18.46, this is acting opposite. Okay, so R2 is equal to 0, R3 is equal to 0, R4 is equal to minus 11.52 Newton. So reaction unit is Newton. So these are the support reaction for the given problem. Okay, so R1 is equal to minus 18.86. Is anyone you have to answer. Okay, left support reaction, this is the left, this is right hand. Okay, so this is about 3D elements. So here all the problems are same only, so just you have to remind the okay, so here one more thing is after calculating the global stiffness matrix, you have to check the properties of stiffness matrix. Okay, the main diagonal should always positive, so look at these values should be always positive, and it is a vice versa. Okay, so in the case this is all are positive value only. Okay, correct. So it is a symmetric matrix, so minus 7 point minus 7.00. okay, so such type of, if you have got, if you what, if you know, if your properties applied correct, means this is correct. Okay, otherwise you have to resimplify this here only. Okay, don't go for next steps. Okay, so that is what the properties of global stiffness matrix. Okay, like this you have to calculate, you have to solve the problems on what? Elimination. This what you have to solve the problems on elimination method by using 2 bar element, 4 bar element. Okay, okay, I hope you understand this problem. Okay, thank you.